Hear me well?
Yes, very good.
Great. Hello everyone, this is Berkay. In this session I'm going to present our work called Dynamic Group Key Agreement for Resource Constrained Devices using blockchains. This is a joint work with Orhan Ermiş, Gürkan Gür and Fatih Alagöz. As an outline of this presentation, we will go first with the background of Group Key Agreement protocols. Later on, I will present our motivation to build this protocol. Later on, we will get into detail of our scheme, and we will go through security and performance evaluation of our scheme, and we will finalize with conclusion and future work. So, as a background of the Group Key Agreement protocols, the key purpose of this protocol is that in an insecure environment, the multiple participants needs to agree on a shared secret key. This is a key requirement, and in that scheme there should be no centralized entity, and all the participants needs to communicate with each other, and doing that they need to establish a common secret key. There are two kinds of Group Key Agreement protocols. First one is static ones and the dynamic ones. The dynamic ones differs from the static ones with the auxiliary operations. What does that means? That when a participant joins or leaves from the network or from the group, only the protocol is partially performed. This increases the performance of these auxiliary operations. There are several security properties that need to be assured while designing this kind of protocols. Is that authentication, fault tolerance, forward secrecy, and forward and backward confidentiality. We will go into detail with these properties in later sections. So, as a background, it all started with Diffie and Hellman, which introduced a key agreement with two participants. Later on, Ingemerson et al. Has introduced multiple key agreements with N-1 rounds. And later on, Diffie has solved man-in-the-middle vulnerability using authentication feature. And Burmester and Desmet has introduced more efficient algorithm. There are also tree-based, cluster-based, asymmetric protocols has introduced. And as a use case of these protocols, which as an example can be vehicular adapt networks and even body area networks. So as our motivation is that because of the decentralized characteristic of these Group Key Agreement protocols, each participant in these groups needs to verify each other. For example, if there is n participants in the group, any participants needs to verify n-1 participants in the network. Because of that, they need to establish a communication with all the participants in the network, which creates a communication overhead. And also during the verification stages, these participants needs to store all the key materials in local storage. Because of the given properties explained above, it is very hard to implement these mechanisms for the resource restricted participants. So what is our scheme? Our scheme is a blockchain-based Group Key Agreement protocol, which is based on CAP-BBC. And we have used, as a blockchain platform, we have used Hyperledger Fabric platform. Hyperledger Fabric is first developed by IBM, and later on it's adapted by Linux Foundation projects. So we have migrated the verification overhead from each participant to the blockchain network. And the participants only needs to communicate with blockchain network during the key computation stages. And as a result, all the keying materials are now stored in the blockchain ledgers. So let's get into detail of how the Hyperledger works. Hyperledger Fabric differs from related schemes with the only specific subset of peers needs to perform execution during the validation stages, before the validation stages. only endorser peers perform the simulation of the transaction and the client collects them, and afterwards they produce read-write sets, how the ledger is changed according to this transaction. Afterwards, there is an ordering stage and validation stage. In ordering and validation stage, the consensus mechanism is implemented, and the faulty transactions are eliminated. If all is okay, the output of the transaction is disseminated to all the peers in the blockchain network. So the fabric peers simulates transactions and maintains the ledger. Order performs consensus. A ledger maintains the blockchain ledger. Fabric chain code is the application that performs transaction simulation. It is like a smart contract in other platforms. And endorsement policy defines set of organizational peers for the transaction validation requirement. For example, there can be multiple organizations in the system, and endorsement policy can say that at least one peer from each organization should verify this transaction. And when the client sends a transaction, it should send to endorsement peers that fits this endorsement policy. So how this transaction flow works. From the left-hand side, there is a client which prepares a transaction proposal. It sends to simulator peers. They simulate, they create read-write sets and return back to the client itself. And then client creates actual transaction request, send it to ordering service. Ordering service perform the ordering, perform validation. If it is all okay, it disseminated to all peers, including non-endorser peers. So how our scheme works. From the left-hand side, there are the participants which performs actual key computation. They use Hyperledger Fabric SDK in order to interact with the network. There are peers, there is an orderer, there is an Hyperledger Fabric certification authority which verifies the identities of these entities in the network. As a definition, we represent each participant as UI. There is a participant list which consists of two subgroups, which are UNet and UGroup. UNet is participants that resides in the blockchain network, and UGroup represent the participant which actually computes the group key. And each participant who fully follows the protocol is called honest participant. And the participants who performs the key computation is called UGroup again. And this is a circular group which at the end of this group, the first participant comes next. So how this protocol works? The blue ones is the blue ones is performed by UGroup, and the yellow ones performed by UNet. First of all the group participants perform group key, temporary public key generation and distribution with these network participants. Network participants then verifies these temporary public keys and perform fault detection. If after the faulty participants are eliminated from the network, group participants query for the next participant in the list. Let's next participant temporary public key from the list. Later on, there is a secret key generation and distribution stage. In this stage, all the group participants generate temporary secret keys and distribute it with the network participants. Afterwards, again with public key verification, there is a secret key verification stage and fault detection stage. Afterwards, all the secret keys are stored in the ledger. Now the group participants can query for these stored secret keys. So if this secret key, after these secret keys are queried by the group participants, they can compute the actual group key. If there is a join or leave operation occurs, only subset of these steps are performed for specific participants. So in our model, we have isolated the ledger with the Hyperledger fabric channels. This provides the ledger isolation within the network. In this case, we can share this shared secret keys, temporary secret keys between those channels. These channels, each channel is represented by network participants. We can also call them as organizations. So, since we distributed temporary secret keys between those organizations, organization cannot compute the group key without colluding. So, as I have mentioned before, there are some security properties that we need to satisfy. First one is the authentication. Because Hyperledger Fabric platform is all the entities in this platform needs to be identified before joining to the network. For example, clients, peers, orders, all of them should be identified. And as an additional layer of authentication, we use signature schemes with long-term private, long-term key pair. So as a fault tolerance, we remove malicious participants during the protocol execution, and the protocol can continue without any problem. As a forward secrecy, also called perfect forward secrecy, long-term private keys are only used for authentication. They only use for signatures, not for key computation stages. So as for the auxiliary operations, backward and forward confidentiality is also very crucial. For example, when a participant joins to the group, they should not be able to read the messages which is shared previously. Again, when a participant leaves from the group, it should not be able to read the following messages in the group. So we do it by recomputation of temporary private keys if any auxiliary operation is occurs. So as a security attacks and mitigation, for the impersonation attack, we use, as I mentioned, we use signature schemes. For the eavesdropping attack, it is very hard to capture private keys from the shared variables because of the discrete logarithm problem. And we add timestamp variable in each message during the message transmission, which in this case we can check this timestamp against the replay attacks. So as a security model, honest but curious adversary says that a participant has no other choice but following the protocol, but it can listen all the data is transferred within the group and try to manage valuable information out of it. In our case, a network participant is bounded to chain code implementation, which is verified by all the organization in the network. So they cannot exit it from this protocol implementation. Because of that, our security model fits to honest but curious adversary model. So as a performance evaluation, we have used computation complexity and transmission complexity for each participant. For the computation complexity, we have used exponential model operations, which are mainly used during the verification stages. Because in our protocol, the group participants does not involve in the verification stages. Blockchain network performs this. Because of that, we can say that our computation complexity for each participant is O1. And again, for the transmission complexity, our participants in the network only communicate with the blockchain network. In this case, we can reduce the communication complexity dramatically. So we have also implemented this protocol and performed performance comparison with our model, the model that we have built on top of it. As you can see here, as we increase the number of group participants in the network, the time of the group key computation increased dramatically with the CAP PVC. On the other hand, with our protocol, it increased linearly. The reason is that, as I have mentioned, that the computation complexity and transmission complexity is much lesser than other protocols. So as a conclusion, we have decreased the computation overhead from ON to O1 for each participant. Total number of network transmissions during the key computation is decreased from ON squared to ON. We have stored all the authentication parameters in the network participants in the blockchain network, and we have eliminated the group key computation capability of network participants by isolating the ledgers by using the channels. As a future work, we can utilize different consensus protocols and membership service providers of Hyperledger Fabric, because the Hyperledger Fabric architecture provides a modular structure that we can replace each component with future extensions. And again, another possible future work can be, we could utilize trusted execution environments for both simulating the transactions and storing these keying materials. In this case, even organizations, if collude to compute the group key, they cannot see the actual data resides in the trusted execution environment. Thank you very much for your listening.